My name is Yu, and I'm a graduate student here at Caltech, and I have titled this presentation very broadly as Hydrated Sulfates on Mars, so moving away from Gale Crater. So we have seen sulfates from orbit as this large-scale layer deposits, and then from in situ investigations, so this is from the Perseverance rover at Jezero Crater, they appear as smaller millimeter-scale pore-filling phases. So there are many open questions about hydrated sulfates on Mars, and I see that the formatting is a bit messed up here. But so the first one involves the thermodynamic stability of these phases of hydrated sulfates, which are in thermodynamic equilibrium, and what do they say, what do they tell us about the environmental conditions of Mars? The second relates to the source of sulfur, so how widespread were the sulfate-bearing waters that led to the precipitation of sulfates in ancient Mars. And the third is how can we connect the stoichiometric hydration states of the sulfates to the bulk water content of rocks, which have implications for understanding the contribution of hydrated minerals to the overall water budget. So I will focus mostly on the first question in this presentation by looking at the sulfate mineralogy at Jezero Crater and only very briefly touch on questions 2 and 3 towards the end of the presentation. But before that, let's look at some of the puzzling observations that have motivated these questions. So the stable phase of hydrated sulfates at a given temperature and relative humidity condition can be predicted by thermodynamics. So here is a phase diagram of the hydrated magnesium sulfate system at different temperature and relative humidity conditions. And we see that at the environmental present-day conditions of various landing sites, including Viking, as well as Gale and Jezero Crater, thermodynamics predicts that the stable phases of magnesium sulfate at the surface would be absomite, starkite, as well as amorphous magnesium sulfates. But we know that these hydrated sulfates can also readily change to their thermodynamically stable phase in response to changing humidity and temperature conditions. So this is observed in Earth as well as on Mars. So on Mars specifically, it was observed that the warm conditions in the Chemin instrument on the Curiosity rover, which is between 6 and 30 degrees Celsius, drives the dehydration of the collected gypsum samples. So these blue bars decreased over time, while the basanite, which is the yellow bars, increased over time. And yet from orbit, it has been seen that there is frequent occurrences of the coexistence of layered sulfates of monohydrated and polyhydrated sulfate layers. So as we have seen previously, that the sulfates tend to convert to the thermodynamically stable phase at changing hydration conditions. It is puzzling how two sulfates with very different hydration states can coexist in the present-day arid Mars environment. So the geologic history of the deposition of these alternating sulfate layers is puzzling, but it is likely that the uncertain impacts of kinetics in the formation of these alternating layers of sulfate with different hydration states. And while the hydrated sulfates have been studied with both orbital spectroscopy as well as in situ rover investigations, it has only been the hydration states as well as the cations of the sulfates have only been determined with high confidence recently with the Curiosity rover and more recently with the Mars 2020 Perseverance rover as well. And so let's now look at the hydrated sulfate mineralogy at Jezero Crater and what that tells us about the thermodynamic stability of these sulfate phases. So at Jezero Crater, we do not see sulfates from the orbit, but as we will see in this presentation very shortly, hydrated sulfates have been detected in the Jezero Crater floor, the Jezero Western Fan, and more recently in the margin as well. So we have looked at the hydrated sulfate with the Sherlock instrument, which is a Raman and fluorescence spectrometer. And so Sherlock uses a 248.6 nanometer deep UV pulse laser excitation source to generate the Raman spectra, which we have used to identify the hydrated sulfates. So here is an example of the hydrated sulfate Raman spectrum, where we can see a sulfate sharp peak at about 1,000 wave number and a broad hydration feature at 3,000 to 4,000 wave number. So what we learned about calcium sulfates at Jezero Crater is that the dominant form of calcium sulfate is anhydrite. So anhydrite has been detected in all geologic units across Jezero Crater, from the igneous crater floor units to the sedimentary western fan front and the upper fan as well. Hydrated calcium sulfate basanite has been detected only in one target in the stratigraphically higher upper fan unit across the crater floor and the western fan, but has been detected at an additional target in the margin unit more recently. While these anhydrite is sometimes variably mixed with hydration spectral features in the Raman spectrum, they don't correspond to signatures, hydration signatures of gypsum. And these hydration that is mixed with anhydrite is likely due to hydrated magnesium sulfate. So it is interesting here that we see the coexistence of anhydrite as well as, which is an anhydrous form of calcium sulfate, together with the hydrated form of magnesium sulfate. So this means that we do not detect gypsum at Jezero Crater, which contrasts with the detections of gypsum at Gale Crater. And this difference could be due to the differences in the sampling depth at Jezero Crater, which is shallower and closer to the surface, where gypsum is not expected to be the thermodynamically stable phase. It could also be related to how there is a lack of larger centimeter scale veins detected at Jezero Crater, which could create localized conditions that stabilize this gypsum rather than basanite, which is expected to be the thermodynamically stable phase at the surface at Jezero Crater. But other than basanite, there has been many hydrated sulfates that have been detected by Sherlock, as represented by these circles in this plot here, which is a plot of hydration peak position as a function of the sulfate peak position that we obtained from the Sherlock-Raman spectrum. So these points here of the Sherlock measurements span a wide range of sulfate peak positions as well as hydration peak positions. And when we look at the Raman spectrum of these hydrated sulfates, we see that they have variable peak shapes as well in different targets from these different geologic units. So to understand what these spectral variation mean, we turn to lab data where we know what is actually going on better. And so which are incidentally also included in the plot that I had just shown previously. So here I have taken out the Sherlock measurement points, and what is remaining in this plot is the colored shaded region represent the range of hydration and sulfate peak positions of different sulfates that have been measured in the lab. So in general, the more hydrated sulfates will plot to the left of this plot with lower sulfate peak position, and the colors represent the different cations, so blue for iron 2, pink for magnesium, orange for calcium, green for iron 3, and purple for iron magnesium sulfate solid solution. And so I'm going to add back the Sherlock measurement points to this plot. And the first thing we can see is that there's negligible detections of Sherlock measurements of highly hydrated sulfates. So this is in contrast to the predictions of thermodynamics here, where we see that the environmental conditions at Jezero Crater could indicate the formation of absomite. Turning our attention instead on what we actually see. So we see that these many points can be classified into 4 different clusters of hydrated sulfate spectra type. And so the first one is this big cluster here that is made up of points from the crater floor in green, the fan front in pink, and the upper fan in orange. And these points are consistent with magnesium sulfate with 2 to 5 water. There are some points out here from the western fan which plot at higher sulfate peak position, and so they imply the presence of magnesium sulfate that is less hydrated. The third cluster here is consistent with the calcium sulfate, which are the hydrated calcium sulfate basanite that I had just talked about. And finally, there's another large cluster of points here that plot at low hydration peak position. And this cluster does not significantly overlap any phases that I have included in this plot, but could be amorphous sulfates, which have been detected at Gale Crater, but for which lab data is lacking compared to the crystalline sulfates in this plot. And so what do these sulfates tell us about whether they are in thermodynamic equilibrium or not? So here again is the phase diagram of the hydrated magnesium sulfate system, and we see that at Jezero Crater conditions in green here, thermodynamics predicts phase changes between absomite, starkeyite, and amorphous magnesium sulfate. But lab studies have shown that the hydration kinetics of these magnesium sulfates are prohibitive over diurnal and seasonal timescale. And so the detection of these mid-hydration magnesium sulfate is consistent with the predictions of thermodynamics, and we think that they are in equilibrium in the present-day climate. In contrast to that, the low hydration magnesium sulfates are not in equilibrium in the present-day climate. So magnesium sulfate monohydrate, or kieserite, is stable at high temperatures of greater than 50 degrees Celsius. The direct precipitation of another sulfate that we have observed at Jezero crater, which is calcium sulfate anhydrite, also requires high temperature of greater than 50 Celsius. So the detections of these out of equilibrium phases mean that processes that are not thermodynamically and kinetically favored are required for their formation. So there are two ways that these out of equilibrium phases can form. The first is if there was a high temperature environment at Jezero crater at the time of formation, but there is no geological evidence that suggests that is the case. Instead, we favor the hypothesis that these phases form from a low temperature fluid of high salinity. So here is a simple conceptual model that describes how these out of equilibrium phases formed. This is based on the lower solubility of calcium compared to magnesium sulfate, as well as the thermodynamic considerations that I have just talked about. So in this model, anhydrite is expected to precipitate first due to its lower solubility, and the more soluble magnesium sulfates will precipitate as the fluid evaporates. And this is consistent with Sherlock observations, where we see that magnesium sulfates is concentrated in the stratigraphically lower crater floor. And the out of equilibrium low hydration magnesium sulfates that have been detected can be explained by the presence of calcium sulfate anhydrite, which have been shown to be able to create local conditions that stabilize these out of equilibrium magnesium sulfate phases. And so just to conclude, based on thermodynamic considerations, we see both in equilibrium magnesium sulfates as well as out of equilibrium low hydration sulfates, which we infer to mean that there was deposition of salts from low temperature, highly saline fluid. And just briefly touching on questions 2 and 3, so sulfate has been observed in every landing site so far, even when not seen from orbit, like Jezero crater. But the small pore-filling sulfates at Jezero crater are different than the large-scale layered sulfates. So what does this imply for the sources of sulfur across the different landing sites? And finally, it is ideal if we could connect the stoichiometric hydration states of these sulfates that we have constrained with the Perseverance rover, but it is not straightforward to infer how much they are sequestering water into the bulk rock, and so we need more lab studies to understand how these different water is expressed across different instruments. And that is the end of my presentation. Thank you.
Questions to the microphones?
I'll ask one while other people are pondering. You showed nicely, on your plot, you had iron sulfates and iron magnesium and then magnesium. Yes. And so I was wondering, how do those mixed phase iron magnesium sulfates work with your story for the others? Is there thermodynamic data available for those, or can you predict how that might behave, or is that something for the future?
I'm not sure that there's a lot of thermodynamic data on these mixed phase iron magnesium sulfate, but what we can see here is that there's not a lot of points that plot within this iron magnesium sulfate solid solution, and this could be related to how Sherlock, which uses the 248.6 deep UV laser, is less sensitive to iron-bearing phases, and so it would be interesting to see, to consider the thermodynamic stability of mixed phases, because we do expect there to be mixing, but it's not clear how they can relate back to our Sherlock detections.
Hi, hello, this is Germán Martinez from the Lunar and Planetary Institute. So this is a comment on the right figure
Yes.
on temperature and relative humidity at Gale and Jezero. I think that those values are an upper bound for the relative humidity in the sense that those are estimated values, assuming that the water content is constant in the first meter. Because what we are measuring at Gale and at Jezero is the humidity at 1.6 meters. In other words, those values of humidity at the ground are an upper bound, and possibly the values are, like lower because they're absorption at night. So just as a comment, right? Like very likely the values will be, like towards the left, towards lower values of relative humidity. And I think that the difference in Gale crater versus Jezero is because those Gale values, if I will remember, I think that represents Canaima, but then the overall values at Gale crater are more in line with Jezero. So it's not that Jezero is colder, I think those values are for Canaima, if I will remember.
Okay, thank you. I'll look into that.
And I think we're going to have to move on from here.
Okay.